Good morning to colleagues joining us, and welcome to our webinar this morning, the fourth in a series of technical webinars. I know some of you have been able to join us for the previous webinars in this series, and we've had some really interesting discussions, and I'm quite sure that today's webinar is no different. I'm looking forward to learning a lot and finding out more around signalling and all that goes with that. As always on these webinars, we're delighted to be working with Ralph Goldney from Railway Consulting, who's going to be taking us through the webinar today. He's joined today by Adam Saunders and by Nigel Harris, who are going to be working with him. I'll let Ralph do the full introductions in CVs in due course, but delighted to have you with us today. And thank you for giving us your time. As always, we are recording this webinar. That means it will be available on our YouTube channel probably later today, or certainly by the end of the week. So if you have to duck away, or if you want to share it with colleagues, please do. You'll be able to find that online later. And you can also see the other webinars in the series also on our YouTube channel if you've not been able to pick them up, and indeed other webinars on a range of topics that we've been hosting as RFG over the last few months and indeed now years. Just whilst a few more people come, let me just remind you that there is time in this webinar for question and answer. So if you've got questions, please do put them into the Q&A box or into the chat, and we will pick up as many of those as we can at the end of the webinar. It doesn't really matter which one you put them in. The Q&A is slightly more obliging, but if you can't see that, please do just drop them into the chat and we will try and pick them up. If you want to get a copy of the slides from today, that's great. Just drop Yvonne or myself an email and we'll get those slides over to you later today as well. So I think that was all I wanted to say by way of introduction. Really delighted then to welcome Ralph for webinar number 4 of this series. A well-trodden path now, Ralph, I think, but let me hand over to you to take us through the rest of today's proceedings, and many thanks.
Thanks, Maggie. Hello, everybody. Oh, it's nice to be with you today. We're going to talk today about signalling and train planning process. You may wonder just how relevant the signalling part, at least, of this is to the rail freight world. And this is a photograph that I took, 2 photographs that I took when Adam and I, our co-speaker here, did some work for ABP at Hams Hall. And the left-hand side, you can get to see our speaker in side profile inside the relay room at Hams Hall. Now, this is ABP property, and it makes the point that actually in 1 or 2 locations, there's actually quite a lot of signalling that's actually within the rail freight estate. And on the right-hand side, we can see that the signalling masts here with the HH3 and HH5, Hams Hall 3 and Hams Hall 5. If you've got nothing better to do as you go around the network, it's good fun to look at the signals and work out what the letters stand for. Well, I find that, but then again, that's me. And this shows the estate with the signalling. So it's a very real thing for the freight estate. And we're going to talk about taking that forward, how that works into the train planning process. So we're really fortunate actually to have 2 very experienced speakers. Adam runs his own business, Reznet, with over 50 people working for him, working on a variety of freight schemes across the UK, mainly in the UK, but also internationally. He's worked in signalling all of his life. He knows more about it than 5 seminars could cover, but he's agreed to give us an overview. And as I say, he and I have worked together in the freight estate, so he's very familiar with the uses of freight. We like to have a doctor in the house, and today we've got Dr Nigel Harris, PhD in rail operations. Nigel is the managing director of the Rail Consultancy, which provides a lot of operational and train planning support, and probably much more than that, to both TOCs and FOCs. Nigel's a very experienced practitioner in this area. So that's great. We've got some really good speakers today. We're very fortunate to have them. So with no further ado, I'll crack on and over to Adam to talk about signalling, if that's okay.
Thank you, Ralph. Cheers. Good morning, everyone. So I've got a few slides just to give a very high level overview of how railway signalling works. I've only got a short amount of time. I could talk for hours or days on railway signalling, but I'll try and keep it short and quite a high level overview. So the first slide that I've got here is talking about block working. So all railway signalling works on some form of block working. And when I say block, I mean a block is a section of line that only one train is allowed into at any one time. Obviously to keep trains apart and stopping them coming into conflict with one another. Block working has sort of evolved over the years. In the very, very early days of railways, the block working wasn't controlled by signals. It was started off with a timer, and they'd let one train in, and then 5 minutes later let another one in, which, as you can imagine, led to a few incidents. So we've moved on now. So the diagram shown above is for 4-aspect signalling. So basically the signals have 4 aspects: red, yellow, double yellow and green. And the top line there shows you the aspect sequence. So train number 1 has just passed the signal on the right hand side, which has gone to red. The next signal is at yellow. The following signals at double yellow, and the next signal is at green. So we want, and Nigel will probably touch on this, we want trains to run on greens all the time. That's the most efficient way to run trains, because they're running at full line speed and they don't have to brake and accelerate. So you try and keep, in 4-aspect sequencing, you try and keep trains 4 block sections apart, or 3. So if a driver experiences a green signal, that's okay to proceed at full line speed. Double yellow means the next train, the next signal will be a yellow, and the one after that will be a red. So in 4-aspect territory, trains normally start braking when they see a double yellow, and then obviously yellow then to red. 4-aspect signalling is probably currently the most efficient, the way of getting the most amount of trains down a single line at any one time. And this is what we call headway, so we can get more trains down a track. So 4-aspect signalling is used on main line, so it'll be on the East Coast main line, West Coast main line, etc. If you don't require such a high train frequency, you can drop down to 3-aspect signalling and 2-aspect signalling, where you can keep the trains further apart. So going back to 4-aspect signalling, the distance between the double yellow and the red is the braking distance for the trains. So that's why we have 4-aspect signal, so we can bunch trains up closer together. But if you've got a branch line where you've got one train every half an hour or something, you just have 2-aspect signalling, where you can just have the same braking distance, but you just work off a yellow to red rather than double yellow to red, and it's more efficient. Obviously, the more on 4-aspect signalling, you've got to put more signals up, and putting more signals up costs more money. And then the final point on this is the spacing of the signals is obviously determined by the brake, is determined by line speed. The gradient, obviously it takes trains longer to brake when going downhill than going uphill, and also as well the braking capabilities of the rolling stock. Network Rail uses a variety of stock on the same lines, so you've got to allow for the worst braking stock or impose speed restrictions on that stock. So that's sort of an overview of block working. I think there's any questions. Yeah.
So just to say that, just to reflect there. So really, it's all about braking distance, isn't it? And the thing about braking distance is line speed, gradient, and braking capabilities. Yeah. And so what you're saying is, in this aspect, the double yellow, that's the braking distance of that you need to be able to hit. Yeah. So the distance from the double yellow signal down to the red is the braking distance. And in the 3 aspect, you wouldn't have the double yellow. Is that correct? And
Yes,
basically, when you hit the yellow, you have to put the brakes on, assuming the next signal is going to go.
Yeah.
Okay, thank you.
Yeah. So this next slide is talking about train detection. So as we saw on the previous slide, when a train goes past a signal, it replaces the signal to red. And to do that, we need to know where trains are at all times, not just for replacing signals, but for clearing signals as well and allowing points to move, etc. So train detection is a fundamental part of railway signalling. In the little diagram, top left-hand corner is a sort of diagram of a basic DC track circuit. And this is the simplest form of track circuit. It was the earliest used, and they're still in use today and still being put in use today. They're simple, but they're effective. So effectively, you have a battery, or in other areas, you have that battery would be derived from a power supply that goes through a track feed set, and then that applies a voltage to the rails, normally about 12 volts. The voltage then, because rails are made of metal and are conductive, that voltage will run through the rails till it gets to the other end of the rails, where it then goes off a lead and passes through a track relay. So for those of you who don't know what a relay is, relays are used all over the railway. So they're a unit that when a voltage is applied to the coil, it energizes a magnet, and then that magnet forces the contacts up. And then when the voltage is taken off the coil, they drop back down again. So there's a series of contacts that prove whether the coil's energized or not energized.
So we can think of a track relay effectively as a switch that's off when there's power and on when
So the current runs through the rails, through the track relay, and then back to its original power source. So it basically it creates a circuit, i.e. track circuit. The circuit is defined by insulated rail joints. So obviously, because rails are metal and they conduct electricity, we need to break the rails into sections, and we do that with an insulated rail joint, which you can see in the bottom left photo. So it's a piece of nylon that provides a physical non-conductive separation between the rails. So the tracks, so wherever you see an IRJ like that on the track, you will almost certainly find track connection leads either side of it, either to a track feed or a track relay. So we've now got our nice circuit running between our insulated rail joints from a battery through the rails, through a relay, and it's all sat there nicely energized. And then along comes a train. So because the axles on a train are also conductive, as soon as an axle enters that section of that circuit, the axle of the train acts as a short circuit. So it takes, so that obviously electricity always wants to take the path of least resistance. So the electricity goes through the axle of the train and back to the battery. Therefore, there's no current flowing over the relay anymore. So the relay drops, therefore telling us that there is a train on a section. But this is the important thing. A track circuit will only prove that the sections is not occupied by a train. It doesn't prove there is a train on there, because they're fail-safe. So if the fuse blows or anything, the relay would drop as well. But that doesn't mean there's a train there. It just means there's one not there. So that's a very basic track circuit. Track circuits have moved on over the last 20, 30 years, probably longer than that, where you can have frequency track circuits. So insulated rail joints cost a lot of money to install and maintain, and they also alter the ride for passengers. When you're on a train and you get the dun-dun, that's where you're going over rail joints. rail technology's moved on quite a bit over the years, where you can now have massive lengths of track. So we don't want to ruin that by putting rail joints in. So there's what we call frequency track circuits now, where same principle applies. We apply a voltage to the rails, and we have a track relay, but the frequency of each adjoining sections is different, so that the frequencies can't interfere with each other. So basically you have an invisible insulated rail joint that's made up of frequencies. Quite clever stuff, made by guys in white coats in labs. Not that I understand that kind of stuff, but we know how to apply it. And then also as well is the advent of axle counters. So axle counters, rather than monitoring the whole section of the track like a track circuit does, it just monitors the extremities of that section. So you have a wheel sensor, which you can see in the bottom right corner there with the yellow thing, and that essentially is fed off to a computer. When a wheel goes over that wheel sensor, it will know what direction that wheel's travelled, and it will count each wheel in or each axle into that section, and then it will. And then the moment the first axle goes over that sensor, it will send the section to occupied, and it will not clear that section until one of the exit wheel sensors has counted out the same amount of wheels that sensor there counted in. If that makes sense. So they're quite popular now because they can work over huge distances. Track circuits are limited by length because you get volt drop where axle counters aren't. You can have axle counters over kilometres, and also as well, they just clamp to the rail. So again, they're not interfering with the rails. So yeah, one disadvantage of axle counters is when they fail, because if a track circuit fails, maintenance can go out, correct it, and it just corrects itself by remaking its circuit. Where axle counters don't, because they don't monitor the whole section, unless you can physically, because the signaler can't see the whole section. You have to do a reset restore process where a sweep train has to go through and inspect the line. But apart from that, they're pretty good bits of kit. Axle counters, and they're becoming more and more popular on the UK network. So that's train detection. And then just moving on to signal boxes. So obviously we've talked about the signals in the first slide. We've talked about train detection. We haven't covered points, but points move trains from one line to another, and they have to be detected, etc. And all of that forms a signalling system. That signalling system has to be controlled from somewhere by somebody. And that is what we call a signal box, where a signaller is located. So again, like all signal boxes have evolved over the years. So going back to the early dawn of railways, signal boxes would have looked like the ones on the left, the one on the left there, where you've got a small box with a lever framing. And because early railway signalling wasn't electric, all signals were semaphores. So you've probably seen the semaphore signals that like a bar that go up and down rather than a light. They're all mechanically operated by a wire. So the area that a signal box could cover was limited by how strong the signaller is to pull a wire over a certain amount of meters to clear a signal or move points. So signal box, you would have on a section line, you would have a signal box like that basically at every junction or at every station to control level crossings, etc. There are still signal boxes like that. There are a lot of signal boxes still like that in use today. They run lightly operated lines, and they're still good for what they do. There's still a lot of them. As signalling became more advanced and more sort of run by electrical circuits and electrical signals and electrical points. We moved to power signal boxes. So that's a picture there of New Street, Birmingham New Street power box, which has recently been decommissioned actually. And inside there is, sorry, and below there is a picture of the panel that is inside that signal box. So that panel would have controlled all of the controls, all the approaches into Birmingham New Street for a considerable distance. Under the control of that signal box would have been a number of signalling interlockings. So a signalling interlocking is probably what one of the local signal boxes would have controlled years ago, i.e. a junction or something like that. And that would be made up of modern signalling using relays or computer-based interlockings. And those signalling interlockings talk back to this power signal box. So power signal boxes can control vast, much larger areas than your conventional local signal box. So again, becoming more cost effective. And these were put in the 60s and the 70s, and they're still going strong today. And then we've now started moving to railway.
We just ask what TDM stands for. Sorry to interrupt.
Yeah, no problem. So TDM is a time division multiplexer. So it is a way of communicating non-vital signalling circuits over telecoms networks, etc. So the local signalling interlocking is a vital system, SIL4, safety integrity level 4, that controls the movements of the points and the signals, etc., to make sure that trains don't come into conflict with one another. But they're requested to move by the signal box. So the request to set a route over a set of points or clear a signal is non-vital. It's only a request. The signalling interlocking will decide whether that's safe to do so or not. So the connection between the local interlockings and the signal box can be carried out over a TDM, which is a non-vital system.
Just aware of the time, actually, Adam.
Yeah, sorry.
That's right.
Yeah, and then we moved on to railway operating control centres. So these are a much improved upgrade on power signal boxes. That picture there is the one of York Rock. So York Rock now, I think, basically controls all signalling on the East Coast Main Line from King's Cross all the way up to York. So that's a vast area. The picture below is the workstation. So there's just one signaller there working it. You can see on the screens a lot of signalling, and you have what you call pods. So that there's probably about 6 of these desks controlled by a supervisor. Then you'll have another pod that controls another section. So it's all done over VDU based computer systems now, rather than push button panels like the New Street box there. Yeah, so Network Rail's plan is to close all the power signal boxes and move them into these operating centres. And then my last slide is the future of signalling, so ETCS. So I've just talked about conventional signalling. You may have heard of ETCS or ERTMS. So ETCS is the signalling element of ERTMS. And there's 3 main levels that are provided on the continent and looking to be provided in the UK as well. So level 1 is pretty much conventional signalling. So you still have line side signals, still have fixed block, but it provides increased train protection to what we have nowadays. So it controls the movements of trains up to red signals a bit more better than what we've got now with TPWS and AWS. Level 2, where you've got no line side signals, but they can be retained if need be. And the driver receives an in-cab indication of what the signal is. So it's still fixed block. So instead of having a physical signal at the side of the track, you have an indication to the driver in the cab. So obviously that's more cost effective because you've got less line side equipment. And then level 3, which is the pinnacle of ETCS, where you have moving block. So where I talked before about fixed block, you can only let one train into a section at a time. That's quite restrictive to getting the maximum amount of train frequency on a line. So moving block is where the signalling system over some clever technology keeps the train behind a safe distance from the train in front. So a bit like adaptive cruise control that you have on cars these days on motorways, etc. So
what's Network Rail's commitment at the moment, Adam? What are they saying? Are they moving to level 2 or level 3 or?
It's hard to say. That there's level 3, I think, is some way off, but they're looking at level 2. That it has been delayed, the rollout of ETCS, and there's some people that are sceptical about how far it'll get in the UK, because it's very effective on the continent, where if you've travelled on the continent, they have long high-speed lines that, for the main part, are just plain line, and they just reach stations every now and then. Where if you travel on the UK network, we've got a very different network to the continent, where we've got junctions everywhere.
Yeah.
We've got different types of stock, so it's a challenge for the signalling engineer to get ETCS onto the UK network.
Thanks, Adam. That's great. I just want to re-show this photo very, very quickly. This is the relay room in Hams Hall, and this is effectively a series. Each relay makes a decision, either open or closed. And actually, this is in effect a very, very early computer, where there is a logic that says, I want to move a train from A to B, which involves the following track circuits. Is that track circuit open or closed? Is that track circuit open or closed? Blah, 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 blah. And then this works its way all the way through in a very simple sort of on-off binary way. And I can't remember, Adam, but there were 300 odd relays in this room, each contributing to the management of, I think, 9 signals. And so actually we're all aware of this stuff, but we don't see this stuff. And, actually, Adam and I have been inside another one at Lindsay Oil Refinery, but very, very similar arrangements where you've got racks of these relays, simple magnetic coils, either on or off, and then being aggregated into what is effectively a 1970s, 1960s even maybe, computer making binary yes-no decisions, which make the safety critical decisions that Adam's talked about. And all that stuff that Adam didn't have time to talk about SIL. It's really important about safety verification.
Yeah.
So, thanks, Adam. Sorry, I bumped in, but I just thought folks been interested.
No, that's good. That's good.
Yeah. Okay. And so, Nigel, thank you. Over to you. And immediately, my fault. Oh, there it is. Sorry, Nigel. There you go. Over to you.
Right. Well, Adam's said a whole load of things which are probably more important than some of the people watching realise, because it leads us into a whole load of things about how you might plan trains. So let's take the top of this diagram again. We're coming from the left. As Adam mentioned, for human factors purposes, you want train drivers to see green lights. And the other thing that's important to realise is that, unlike with trucks on a road, we always run the railway such that a train can stop before it gets to the position of the train in front. But that starts having some quite significant impacts on the capacity, and therefore how we put trains in the timetable. So typically in Britain, blocks are about half a mile long if we're old school, or about 800 metres if you're a bit more modern. And therefore you can see that if we require 2 blocks to break a train, typically trains can break in about a mile, something like that. But then look at what we actually want to do, which is what's shown above. We want the train to approach a green signal, which effectively means there have to be 3 blocks between that and the train in front. So if you go and ask signal engineers, people like Adam, what the headway for signalling, they'll quote that little formula there, and it's got 1.5 times the braking distance, because obviously 3/2 is 1.5. And what this starts to show us is the railway loses a lot of capacity because it's really safe. It's safety layer on safety layer, which is great, because we've agreed for hundreds of years that crashing trains is a bad idea. But once capacity goes down, we're going to come on to see obviously the impact that has on timetabling. But it's kind of worse than that, really, because actually this diagram, which we've taken from a website called railwaytechnical.com, actually we lied slightly, because in some ways you could argue the block positions are not under the signals. They're all shunted about 200 meters to the right. There's an overlap, because I'm sure you haven't done it, but you've all seen car drivers drive up to red stoplights and go over that line. Well, we don't want to do that with a train. So we've generally given ourselves a couple of 100 meters of overlap. Then the S in here, again, we look at how people behave. If you're driving a train on a relatively straight line, you can see several of these signals in front of you. Even though the nearest one may be green, you're probably going to at least ease off, even if you don't actually apply the brakes, earlier than you need to, which means you're going a bit slower than you need to. So we've used up a bit more capacity. And the other thing that's worth mentioning for people who sort of think about road vehicles, I mean, cars are typically, I don't know, 3 meters long. A truck might be 7 or 8 meters long. We happily run around the country freight trains which are up to half a mile long. Without wishing to state the damn obvious, when you go along in a train, what matters is not how far behind the front of the train in front, it's how far the back of it is. And clearly, you know, that train itself is half a mile long. You can see that suddenly we're running trains that are maybe 3 kilometers apart, and we're, quote, at capacity, because we got all these safety margins in. So we're using up a lot of the potential of a railway in not only the minimum we need, but actually a whole load of extra safety margins, which, so we'll come to show on capacity. Thanks there, Ralph, if you're driving. So this is an example from a study from Italy, where you can see we've got time on one axis and the sort of block sections on another. We normally draw these the other way around, but never mind, that's Italians for you. And you can see the black lines in the middle of those colours. That's where the train actually is. But of course, we have to set the signal's route in front of the train, and it takes some time to clear behind. So as you go along, you get these blocking time graphs where you can see different bits of the line are being, quote, used, unquote, by this train. Maybe not physically, but they're either in front of it, so we've got permission for a train to go in, or we're still clearing behind. And as you can see, when you get towards the right-hand side there, when we're trying to set a route for train B, the yellow one, we're only just managing to do that after the route's been cleared after train A. So the trains themselves may be several miles apart, but we're just on the verge of one train impeding another. And that's really what we try and avoid doing. Thanks, Ralph. So that would be fine if you only had 2 trains. We run about 24,000 trains a day in Britain, and there's, you know, Clapham Junction with trains all over the place. And this is where this all gets a bit tricky. So we're now going to look about how we're going to do that. Thank you. So, focusing specifically on freight, we have a freight customer who has some requirement. I'd like to move this many hundreds or thousands of tons of stuff between here and there. And you'd typically go to a freight operating company, have a chat with them, discuss how that might be done. How often are we going to run these trains? How long are they? That kind of stuff. And the freight company, the FOC there, can go into see what trains are already running and try and devise a path through the timetable. And we're going to do a worked example in a bit. Now, if you sign up for a long contract, maybe you're a cement company with a 10-year flow, the freight company then goes to Network Rail quite a lot in advance of it starting. And Network Rail has the ability to flex or just kind of bend, if you like, the train paths of other trains. Now, there might be various reasons you want to do that. See, it might be that if I want to run a train for Adam, I could then go to Ralph and say, sorry, Ralph, would you mind if we ran your train 1 minute earlier? Because then I could fit Adam's train in. That's what I describe really as a sort of the deliberate part of this. But Network Rail also undertake simulation, because we all know that stuff goes wrong. And Network Rail is given an industry responsibility for maintaining punctuality. So we're quite keen to know that if we run this extra train for Adam, whether it's going to mess up other people or not. Not in theory, but in a sort of probabilistic day-to-day thing. And the delay ratio there is where we look at the impact of an input delay and see what impact it has on output delays. And what we hope is that a small input delay has not much impact. If you're really unlucky, if a bad delay ratio, and then Adam being 1 minute late leads to 17 other people all being half an hour late, that's the point at which Network Rail go, no, you're not having this train pass. But provided the train pass that's been suggested by the freight operator looks plausible, there is a contractual right to run that train broadly that time between A and B, and that's included in back-to-back contracts with the customer, which is all very well if you've got 10 years. But of course, you might actually only want to run some stuff, for a month. For example, like winter just gone, we thought we might need our coal-fired power stations in February. So what you're going to do? Well, it's broadly a similar process, but obviously we've got less time for us to go around and ask everyone else who's running trains if we can bend them. But we'll find something, and it's kind of available there for a timetable period. As you realise, the passenger timetable tends to change about every 6 months, so we can't quite be sure it's going to happen after that, but we've got a plan. And of course, occasionally people turn up freight-wise with, sorry, I need this now or tomorrow. Now, that's fine. That's the very short-term planning process, but clearly you get what's left over. And if this means you go from A to B and have to be put in a loop and sit there for 25 minutes, that's tough, because we just haven't had the process to find a better path or to ask anyone else to move theirs. And we try and be a bit clever. So on the West Coast Main Line, there are some paths that are strategically left, because we know that quite a lot of people might turn up, but that might not connect on another line. So you don't really want to do very short-term planning if you can help it, because it's likely to take you longer in an inferior path. And that means your operating costs will be higher, because you're paying drivers effectively by the hour, and you're less competitive for your customers because it's going to take longer. But it might mean that literally you can ring up now and get going quite soon. And the point at the bottom there, if you sign up with one freight company and decide after 5 years you don't like them and get someone else to do it, the contractual right you have for a long-term path would just transfer from one of those freight companies to another. So if you do want to sign up in the rail industry for 10 years or something, we can protect your rights. If you need to, for example, to make investments in wagons, which would take a time. So there's sort of more than one timetabling process, which is a bit unhelpful, but that depends on how much time we've got to do it in and how long you wanted to run it for.
Nigel, could I just ask about the flex? So Network Rail reserve the right to flex any path. How much can they flex by? Is it 3 minutes or is it not as simple as that?
Well, it tends to depend mostly between whether you're a passenger operator or a freight operator. And this is Rail Freight Group focusing on that. Sadly, it's likely to be more than that. So if you're a passenger operator and you've got a right, we're expecting to run at 10 o'clock. The point about flex is they can tell you your train's running at 10:01, whether you like it or not. For freight, plus or minus 15 minutes would be quite normal. Clearly, if they want you to come back in 4 hours' time, they're going to have to come and ask you. But flex is Network Rail's right to sort of bend these paths without having to ask everyone everything. But yeah, I think for freight, if you run on the assumption it's plus or minus 15 minutes, that's probably the starting place for that. So you've kind of got a half-hour window where you're, aiming to be in the middle. It's in some ways it's an administrative simplicity, but freight's considered to be a bit more flexible. Now clearly, if actually you are doing a Royal Mail train or something that isn't flexible, you'd probably want your freight company to go to Network Rail and say, actually, this matters to us. Let's agree on a time and stick to it. So it's a bit negotiable, but Network Rail want the right to have as much literally flexibility as possible to how they get more trains in.
Okay, thanks, Nigel.
Now, that's fine, but how do we actually get this train pass? Now, let's go back at the stage. You can't write a train timetable without a whole lot of assumptions. You do need to know how long it takes to get from A to B, and you do need to make some assumptions about how long you want to spend in stations or terminals, and we'll look at those in each. So let's look at the times as you go along. Well, some of the systems you can see reported, and there's actually a very good unofficial one called Real-Time Trains, report things to the nearest 15 seconds. I mean, what you can infer from what Adam said is that actually we know where trains are potentially to the nearest second, because when the first wheel goes into the next track section, we know where that's happened. But, our systems are a bit old in terms of planning. Half minutes are very common. I mean, other railways use tenths of minutes or whatever. But anyway, we're generally at 15 or 30 seconds here. Now, if you were a clever engineer, and I'm not, and you know how much a locomotive weighs and what kind of traction motor you've got in it, you could work out how it's going to accelerate and brake. Yeah, but of course, this all varies by type of train. And where this gets really messy is for each pair of adjacent places. So let's pick the East Coast Main Line, well, it's called Peterborough and Grantham. We need one set of times that if you actually stopped at Peterborough and are going to sail straight through Grantham, another set if you're going to have passed through Peterborough and then stopped at Grantham, and then another set if you've stopped at both, or indeed yet another set if you've not stopped at either. You need a different time. Now, we'll try and keep this simple for now. Broadly speaking, for freight, we have these days two types of freight. Heavier freight is generally described as class 6, and trains will typically run at 60 miles an hour because it's to do with the braking. Lighter stuff, including container trains, typically timed at 75, or even if you're lucky, 90. It's lighter, so the braking's less of an issue, but we've clearly got two different sorts of timings. And then that would be fine if everything was the same. Now, I don't know how many people on the call maybe run a fleet of trucks or have a number of vehicles are the same. They're not. Most train companies will tell you they know differences between specific locomotives. Some were built on a Friday afternoon. Then, of course, although we can time a freight train separately, whether it's supposed to be empty or loaded, if you take a container train, we don't know before we start what's going to be in those containers until, well, we certainly don't have the timetabling process. I mean, clearly, if there's hazardous goods, we get told operating, but we don't know whether we're going to, this box we've got, it's got a 20-ton weight in it or a 2-ton weight. So we can time a train, but I'm quite sure what's going to be in it. And then I won't ask you personal questions about how you drive your car or how your mates drive, but we all know there's some boy racers out there. Now, it doesn't really apply so much to train drivers, but certainly some of them will accelerate and brake more hard than others. So we kind of land it with some allowances here, and we have to work out what numbers we want to put in. Thanks, Ralph. We should probably put in some contingency. Now, the Swiss, for example, just stick, I think it's 6% in everything, very simple. We've tried to be more clever. We have 3 types of extra time we put in the timetable. Now, if you run a freight train from, I don't know, Felixstowe to Manchester, you can be pretty sure that somewhere along the route, Network Rail is doing some track maintenance. So instead of going along at the full line speed, you have to go along a bit slower. The trouble is you don't, on average, know where it's going to be. So somehow we have to put a little bit extra time in to make sure we cover that. Pathing time is if you come to a junction where 2 routes meet, it can be quite tricky making sure that this train comes there and you come, in the right amount of time afterwards. So it would be common to put a bit of extra time at a junction just to make sure you're likely to get through that. And then particularly on the passenger side, there's performance or what we used to be called charter time. We're going to be recorded at particular locations. So trains on the East Coast Main Line, we kind of want them to be on time and to be recorded as on time on Newcastle. So we're going to put some more time in there. So we've got to have 3 dollops. But hang on, we then need to work out where we're going to put those dollops. If we saved all those times up to the end, then we might sort of lose our path halfway along, and Network Rail controllers might put some other train in front. Could also land up with some bizarre things. So we had an example years ago. So passenger services had one from Aberdeen to Penzance. If you've been to Penzance on the train, the last few miles are a single track. And some idiot decided that they put a big dollop of time in there. So we were on time arriving at Penzance. So put a 20-minute dollop in there, which was fine, except that Cornwall County Council then asked the railways if we could run a train sort of 10 o'clock at night to take people home from things. When then officially you kind of can't, because notionally there's this train on this single piece of track, allegedly. So it's really not very sensible. And if you look at your own personal journeys, you may see that the journey from your local station to the local big city takes maybe a couple of minutes longer in one direction than another, and that's because where you see these little dollops being put in. But there's a bit of an art to this, quite frankly, as to how much extra time you want to put in the timetable and where you want to put it. Thanks, Ralph.
Okay. I'm always amazed how my train's late at Milton Keynes but on time at Euston, and I think that's probably
Because there'll be a dollop somewhere.
Mm.
Now, as well as what's physically possible, so Adam described how the signalling system works, and we can look at how a train breaks or not. This what's sensible. If you go and stand in a field next to the railway line or main line, you see a train go by, red, yellow, 2 yellows, green, signals go by, we might be back to a green signal in 90 seconds. So you'll say to me, okay, that goes into an hour 40 times. We could run 40 trains an hour. Oh, yes, not really. Because there's already been hinted, there's all sorts of other things that reduce capacity. I mean, junctions, for example. And we don't want those train drivers, if you think about the very first slide, to be going along and for the signal to be clearing from double yellow to green the second they see it. But there's other things that are just not sensible. And I'll give you an example here. There used to be a junction in Buckinghamshire, in the middle of nowhere, where 2 single lines met. And we did some performance work for Chiltern Railway, and trains were getting late. And we discovered that's because a train was coming along a line and turning left, and another train was timed to go in the opposite direction 30 seconds later. You have to think carefully how this works. You go along in a train, again, statement to the damn obvious, the back of the train comes after the front, so even if the front of the train was perfectly on time to the second, the back of the train could easily be 10 seconds later. And then Adam would probably like 5 seconds for his points and signals to change. Now we've got a train driver sitting at a signal that's 200 meters away. Well, clearly the train is stationary. We can't accelerate that train from 0 to cover that 200 meters in that time. It's sort of theoretically possible, but never going to happen. So let's not plan for it. You'll have the same thing as you approach stations and terminal yards, going in and out of sidings. And the sad figure that was shared with me recently, basically, although there's some generic kind of standards, there are a lot of specific ones, and there are about 100,000 specific rules like this across the railway network in Britain, in terms of you can't turn right here unless it's 4 minutes after they've come that way, that kind of stuff. And that, of course, is where we're very glad these days to have a degree of computer checking in the timetabling process, because I can tell you, if you do that manually, you miss stuff. So we may well draw the path manually, but we will let Network Rail's timetable planners run a little program at Milton Keynes to check we've passed all these rules.
That's great, Nigel. Just need to be conscious of the time now, mate.
Yep. So it's actually harder than you think. So we know we can't run extra trains at Clapham Junction at 5:30 on a Friday afternoon, but there's a picture of the freight yard at Westbury at lunchtime and the queues of trains. So let's go in and see what sort of problems we might have. One precursor to that, because not all trains are the same, it has an impact on capacity. The upper picture here shows what happens, if you like, on the underground, where all the trains are the same. So they can run all parallel to each other on a train graph, which has got time on the bottom there, all parallel, very nice. We can fit them up nice and close together. And hopefully, if Ralph presses the next button, we'll see what happens if trains aren't the same. So here's another hour, where unfortunately we've got a couple of quite fast passenger trains shown with a steep line on our train graph, and this freight train. And suddenly you can see that instead of, I think we had 7 in the top picture, we've only got 3 trains in here. So that what's shown in italics there, an important point for freight operators is that the difference in speed between different trains has a direct impact upon capacity. And that's a very important deduction, which is complete pain, quite frankly, but it's a very important answer. So what we do is we very quickly share with you a couple of examples. Now, this one's both a bit ancient, because when I find a good example, I like to run with it. Between 1994 and 2007, if any of you used Eurostar, when it was opened, it went out of Waterloo. And if we look at a bit of the track network in South London, we've got the line from Victoria to Bromley. It's got lots of tracks from Victoria to Brixton and 4 after Shortlands, and a 2-track section between Brixton and Shortlands, and a loop via Catford. And at Kent House, we've got an opportunity for trains to overtake each other. Now, we had a big freight problem. As you know, we don't make anything in Britain anymore. We all buy it from China. And of course, we've got people like Maersk who turn up with their enormous ships, and we need to start to take stuff away. So they'd previously been delivering shiploads of stuff to Tilbury, and they were looking at accessing Thames Port instead. So they approached Freightliner. There is a freight operator, other is available, with a, can you help us with our train? And of course, if you turn up with a ship with 10,000 containers and we get maybe 40 of them on a train, it's an awful lot of trains. And they deduced they'd have to run one train every hour, more or less continuously, excluding in the peaks. So a train graph was knocked up. Thanks very much, Ralph. There you go. Now, even if you haven't seen many train graphs before, if you look at the bottom here, this only goes from 10 o'clock in the morning till 10 past 11. You can immediately see there's lots of lines there. This was a busy section of track. All sorts of trains on it already. Now you'll notice I've shown the Eurostars there as thick black lines. That's two reasons for that. A, they were important, and B, do remember Eurostar trains were very long. So we've shown them on there. Now what this diagram also shows is something called flighting, F-L-I-G-H-T-I-N-G, where if we can run trains of similar characteristics quite close together, put bluntly, we can fit more of them in the timetable. And the only person who's unhappy is the electrical engineer who has to provide a whole load of power all at once, but that's their problem. From a timetabling perspective, it's really efficient. A couple of Eurostars, then a reasonably fast train, then a slower one, and you can fit more of them in. Okay. And the Eurostars, by the way, can be arranged in pairs because, for example, we can run one to Paris and one to Brussels. So passengers, don't so much need them evenly spaced. But we knew we were going to have a problem with these freight trains. And it was obvious we were going to have to be overtaken. So we got that loop at Kent House. And what you see on a train graph, if the line is horizontal, a train is stationary. So thank you. So people knocked up very quickly. Where you go? It takes about 10 minutes to do that. We could sit there and you'll see in every hour, they sort of identified two different train paths. And Network Rail have a group of managers called the Sale of Access Rights panel, SOA panel, who sit down once a month and go through things, and they were presented with these alternatives. Now, the trouble is, neither of these are perfect. This first one involves sitting at Kent House for quite a long time whilst we get overtaken by 3 trains. Now, the freight operator might have been okay with that, but it's not great, is it? The second one, at about the hour, looking at the beginning of the end of this, we get overtaken by only 2 trains. But what happens if anything goes wrong? Straight away, if our freight train is late, we've screwed up 2 Eurostars. So you can see now we're don't like that. But actually, they didn't like the other one either, for a very important reason that we sometimes gloss over. I don't know how many people on this call do have a Lamborghini or a Ferrari, but I have to remind you that freight trains don't behave like that. They brake slowly and accelerate slowly. Many freight trains in Britain are 1,000 tons. We run trains that are 4,000 tons. So actually, the graph that had been knocked up very quickly here is a bit simplistic. You can't go along at 50 miles an hour and then stop. We don't normally do it, but these lines should really be kind of curved in and out. So very sadly, Network Rail had to turn down all of these paths, and the traffic was put on trucks on the M25 instead, which is probably not the policy outcome. I'm sure it's not the policy outcome that Maggie would like. So we wanted to run these trains, but actually couldn't fit them in.
Let me crack on, Marge, if that's all right.
Yep. Completely different example. When we've got a single track line, so this is the line between Perth and Inverness. We've got some, this is about 100 and something miles long. Also, it goes over some big mountains in the middle. There's only specific places where we can pass trains going in the opposite direction. So Ralph has highlighted there in red, got a section of double track in the middle. And you can see this timetable's generally been quite well written, because most of the trains, we've got the southbound trains going top left to bottom right, across the northbound ones in there. So if we're a couple of minutes late, it doesn't matter too much. Otherwise, please remember, if you have a train on a double track line and you're late, you screw up the people behind you. If you're on a single track line, you not only screw up the people behind you, you also screw up everyone going in the other direction. Because all these crossings that Ralph is highlighting, they may be in a section of track that's only half a mile long. You might have come, well, the sleeper train shown there comes from London, which is 800 kilometers away. It's actually not very likely to be on time to the second, is it? So suddenly we're in this position where we might have to put extra time in, because actually we can't guarantee to get to that passing loop exactly when we want to. And if some of the trains are light passenger trains and some are heavy freight trains, then the timings between these passing loops may not fit anything helpful. I mean, it'd be really good, wouldn't it, if they were like 15 minutes, because we get 4 of them in an hour, but maybe they're not.
That's really great, Nigel. Thank you very, very much for that. I just want to make one observation here, just going back to this graph here. This is one of the main reasons why it's very expensive to make new freight connections, because if we need to put a new connection in here, let's say, then we need to put a new signal in here, and it all daisy chains back down, up and down the line. And this is one of the reasons that it's very expensive to make new freight connections. Is that right, Nigel?
Absolutely, and you know, that's the physical bit. You may also end up screwing up the timetable for all the rest of the day as well. Yeah. If trains are, you know, booked to be going along like that. So, I mean, in summary, we'd like it to be easy, but actually, because we've got a series of safety related signal equipment that Adam described and a formal planning process, planning a railway is not that straightforward. You know, it's not like a truck where you can just set off, and if you screw up other people, it's tough. We don't allow that on the railway. So there's the safety bit and the efficiency bit. And then when we, for example, need to want to make sure that we use our trains efficiently because they're expensive pieces of kit. And then in fact, we've got some drivers to think about as well. That's why, you know, some of us are going a bit grayer than others.
Thank you very much, Nigel. That's really, really, really great. That was really interesting, and we're very close to time here.
Yeah, thanks. Sorry, there was a data connection issue at this end. I trust when digital signaling's rolled out, it works a bit better than domestic Wi-Fi. Yes, so don't forget this webinar has been recorded and is available along with all the other webinars in this series. So I haven't seen any questions come up in the Q&A. Normally at the beginning I would have alerted people of that facility, but since we're very close to time, perhaps it's just as well. So can I thank Ralph, Adam and Nigel, and don't forget, if you do want a copy of the slides, please let us or Yvonne among our team to know, and we can send them on. I did have a question I was going to ask, but I think we'll probably skate over that now. Just time for me to give a couple of parish notices. We are holding our members' spring meeting and barbecue in Southampton next week on the 23rd and 24th of May. So for those of you who have booked, we look forward to seeing you. For those who have not, you better get us notified pretty quickly. And between the 13th and 15th of June, we have our pavilion at Multimodal at the NEC in Birmingham. So if you're going, come along and say hello. Also in your diaries will be our popular awards evening on September the 7th, which entries are open until the 26th of this month. So full details of all our events can be found on our website at www.rfg.org.uk. And at the RFG, it's Christmas all year round. So if you haven't already booked your table for the event of the year, our Christmas lunch, I'm told there might be 1 or 2 tables remaining. Otherwise, you'll have to join the reserve list. So all I think I need to do at the end now is to thank everybody for joining us, and a particular thanks to Ralph Goldney, whose idea it was to put on this series of events. And from the feedback we've had, I think it's been very successful and well appreciated. So I'd just like to pass that back to Ralph. Great. So I hope at some point we'll see many of you at one of our events. Have a good rest of the day. Thank you.